Hey there, and welcome. Today, we're going to dive into one of the most powerful tools in all of mathematics, differential equations. Now, I know that sounds a little intimidating, but don't worry. We're about to see that they're really just a special kind of language, one that we use to describe how pretty much everything changes.
So, let me ask you a question. What do the laws of physics, the design of a skyscraper, and even the way bacteria grow in a petri dish, what do they all have in common? I mean, they seem totally unrelated, right? But believe it or not, they all share a fundamental mathematical backbone.
And that's where differential equations come in. That's the answer. A DFI for short is basically an equation that has a function's derivatives in it. This means instead of just solving for a number, like x, our goal is to find the entire function that makes the whole thing true. It's the language of a world in motion.
Okay, so to get fluent in this new language, we've got to learn its grammar. For D's, it all starts with two key ideas, the order of the equation and whether it's linear or not. You know, these two labels tell us a ton about an equation, and, more importantly, how we're going to solve it.
First up is order. And this one is super straightforward, I promise. The order of a differential equation is simply the order of the highest derivative you can find in it. That's it. You just look for the highest one.
So for example, take a look at this equation. We've got a first derivative, that y prime, but we also have a second derivative, the y double prime. Since 2 is the biggest number we see there, this is a second-order differential equation. Yep, it's really that simple.
All right, next up, linearity. An equation is linear if our unknown function, y, and all its derivatives are, well, behaving themselves. That just means they're all raised to the first power. You won't see any weird stuff like y squared or the sine of y. And trust me, you want to know this because linear equations are way easier to solve.
Now, this formal definition might look a bit intense, but don't let it scare you. It's really just a fancy way of saying what we just talked about. See how all the eggy terms and their derivatives are just chilling on their own? They're only raised to the first power. That's the dead giveaway for a linear equation.
So we know how to classify these things, but what does a solution even look like? Remember, we're not searching for a single number, we're hunting for an entire function, which usually means the solution is a curve or sometimes a whole family of curves. You see, when we first solve a DE, we get what's called a general solution. It has this little constant c that can be any number. Think of that c as creating an infinite family of possible solution curves. But if we're given a specific starting point, an initial value, we can pin down that c and find the one specific curve that's our answer.
Okay, that's enough theory for now. Let's get our hands dirty and actually put this stuff into practice. We're going to look at a few equations, classify them with our new rules, and then we'll see how to check if a function is actually the right answer.
Let's run through these real quick. Equation A, highest derivative is y double prime, so that's second order. All the y's look good, so it's linear. Equation B, highest derivative is y prime, so it's first order. But look at that y squared. That's the classic sign of a nonlinear equation. And for C, we've got a y triple prime, which makes it third order, and it's perfectly linear. See? Not so bad. So, let's say someone gives you a solution. How do you know if it's right? You just check it. It's actually pretty simple. You take the function, find its derivative, and then you plug everything back into the original equation. Here, we plug it all in, simplify, and what do you know? The left side equals 0, which is exactly what the right side says. Boom! It's a valid solution.
And all of this leads us to something really important, the initial value problem. This is where we take a specific starting point to go from that huge family of possible solutions down to the one single curve we actually care about.
Let's walk through this one. We've got y prime equals 4x cubed. And we know that when x is 1, y has to be 5. Okay, so step 1, we just integrate to get the general solution. Y equals x to the fourth plus our mystery constant, c. Step 2, we use that initial condition. We plug in 5 for y and 1 for x. That gives us a really easy equation, and we can solve for c, which turns out to be 4.
And for the final step, we just take that c we found and pop it back into our general solution. And there you have it. Y equals x to the fourth plus 4. This is it. This is our particular solution. It's the one and only curve that solves the equation and goes through that specific starting point. We've gone from infinite possibilities down to a single predictable path.
So we've seen how to use this language of change, these differential equations, to find a unique solution. And this exact process is what's used to model everything from predicting the weather to figuring out a rocket's trajectory. So the question I want to leave you with is this. Now that you know how to find one specific path out of a whole world of possibilities, what kind of real-world problems could you model and predict?